My hypothesis for this series is that a small local model can do useful work if we give it a controlled environment, clear inputs, and a lightweight structure. I'm not trying to prove that a 4B model can do everything. That would be unrealistic. What I am testing is whether small models can handle specific work tasks when the system around them is designed well. So instead of asking, can this model replace a giant cloud AI, I'm asking, what kinds of work can small local models reliably do? And just as important, what guardrails does it need to do the work safely? Today, I'm setting up the Python template for my local AI work agents mini-series. The goal of this series is to test whether small local models can handle real work tasks on a regular laptop without sending private notes, company information, client files, or internal documents to cloud AI tools. In this first video, I'm not building a full agent yet. I'm building the starter template I'll use for future experiments. This template is the foundation for future experiments. Later in the series, I want to test whether a local AI agent can summarize notes, extract action items, clean up messy documents, create daily work briefings, process local files, and help organize work without uploading anything. But before any of that, I need a reliable base. So today's goal is narrow. Can Python talk to a local model through Ollama and get back a clean response? If that works, then the template is ready for the next experiment. A lot of people are tired of cloud fatigue. Every AI tool seems to come with another account, another subscription, another privacy policy, and another question, am I allowed to paste this information here? That question matters at work. A lot of people work with internal documents, client notes, private planning, code bases, or company data that should not be sent to a cloud AI tool. The goal is to test a different lane. Small, local work agents that run on your own machine, cost $0 per month after setup, and only access the files you intentionally give them. That makes this project more like a workbench than a cloud assistant. It is local, it is limited, and that limitation is part of the design. For this project, I'm using Ollama. Ollama lets me run language models locally on this computer, which means my Python project can send prompts to a model running on localhost instead of sending them to an external cloud API. For this experiment, I'm using Qwen3 4B. This is a small model, but it's capable enough to make the experiment interesting. I'm using Qwen3 4B because the series is specifically about testing what smaller models can do on a laptop. So first, I install Ollama. Then I pull the model with Ollama pull Qwen3 4B. After Ollama is installed and Qwen is downloaded, I test the model directly in the terminal. This direct test matters because it separates the setup into layers. If Ollama cannot run the model directly, then the issue is probably with Ollama, the model downloaded, or the local environment. But if Ollama works directly and my Python script fails later, then I know the problem is probably in my project code. And this is where I hit the first kind of funny local AI problem. I asked Qwen to say hello in one sentence, and it went into a full reasoning spiral about the correct way to say hello. So technically the model worked, it just worked a little bit too hard. I'm not going to fix that directly in the terminal right now. I'm going to leave it as a useful warning sign because it shows something important about the model. Qwen3 is designed to support both thinking mode and non-thinking mode. Thinking mode can be useful for harder tasks like reasoning, planning, coding, and breaking down messy information, but it can be an overkill for a basic connection test. For this first test, I don't need deep reasoning. I need a clean response that proves the local model is running. So later when I connect this through Python, I'll add a few guardrails, stricter instructions, thinking turned off, a shorter response limit, and cleanup logic in case the model still leaks thinking text. The setup starts by cloning the repo, which brings the starter template from GitHub onto your computer. Then move into the project folder so all future commands run in the right place. Next, create an active virtual environment. That gives this project its own isolated Python setup, instead of mixing its packages with everything else on your machine. Then install the packages from requirements.txt. In this first version, we only need request for talking to Ollama and python.env for reading local settings. Finally, copy .env.example into .env. The example file can be shared on GitHub, but the real env file stays local and stores the model name, Ollama URL, agent name, and thinking mode settings. Next, I'm going to build the folder structure. I do want to mention that there is no official required way to organize an AI agent project. Different people use different structures. Some use LangChain, others use Autogen, some use custom frameworks, and some people put everything in one file. For this series, I'm choosing a framework-free structure because I want to understand the moving parts directly. This is the structure I'll be working with. At a high level, the app folder is the main agent runtime. Processors handle logic and cleanup. Connectors control access to outside information. The data folder stores local input and output. And the examples folder holds save example files, and the script folder is for helper commands. Again, this is not the only way to organize an agent project. This is the structure I'm choosing because it keeps the project understandable and easy to expand. One important design choice I want to mention here is the split between connectors and processors. I'm thinking of connectors as the agent's sensors. Connectors are how the agent gets access to information. A file connector might read a local note. A calendar connector might read a local calendar export. A weather connector might call an external weather API later. They should not give the agent access to the whole computer by default. That's the privacy boundary. Processors are different. Processors are the logic and cleanup layer. They clean their responses, validate outputs, format data, and guard against messy model behavior. So in this project, connectors answer the question, what is the agent allowed to see? And the processors answer the question, how do we clean, validate, and transform what comes back? The data folder gives the agent a controlled workspace. Inside it, I use folders like data inbox, data processed, and data outputs. The inbox folder is where I place files I intentionally want the agent to process. That is the keyword, intentionally. I don't want the agent scanning everything on my machine. I want a narrow, approved input folder. The process folder is for cleaned or intermediate files. The output folder is for final results like summaries, task lists, or briefings. This gives us a sample path: input, processing, output. I also set up a git ignore. This is important because the project will eventually go on GitHub, but the private local data should not. The repo can include the folder structure, the code, and the example files, but it should not include real env file, the virtual environment, or private files inside the local data folders. That means, as a viewer, you can download or clone the template without getting my private data, and I can use the template without accidentally pushing private files to GitHub. Now I'm going to go over the main agent code. The core file is agent.py. This is the first version of the agent's model communication layer. At this stage, the agent is not using tools yet, it's not reading files yet, and it's not making decisions yet. Right now, it has one job: send a message to the local model and get a response back. The important thing is I'm using Ollama's local endpoint at localhost 11434. That means the flow is Python to localhost, Ollama to the local Quen model, and then back to Python. If that works, our base connection is good to go. For this project, I'm using an OpenAI style chat structure. That means the request is organized around a message, a system message, a user message, and an assistant response. The system message tells the agent how to behave. The user message is the actual request, and the model returns the assistant response. I also create a config.py file. This file reads settings from env. The model name goes there, the Ollama base URL goes there, the agent name goes there, and thinking mode goes there. This keeps the project flexible. If I want to test a different model later, I should not need to rewrite the code. I should be able to change the model name in the env file and keep the rest of the project the same. When I first connected the Python agent to Ollama, I saw the same overthinking problem I had already seen in the direct terminal test. The connection technically worked. Python started the agent, loaded the Qwen model through Ollama, and got back a response. But the response was not clean. Instead of just saying something like, "Hello, local Ollama connection confirmed," Qwen returned a long explanation of what it thought I wanted, how it should answer, and why it should keep the response short. So that first pass proved one thing. Python could talk to Ollama, but it did not prove that the agent was returning a clean, usable response. For a work agent, I don't just need the model to respond, I need the response to be predictable enough that the rest of the app can use it. So instead of showing broken code, I'm going to walk through the working version and point out the pieces I added to fix the problem. Those fixes include turning thinking off, adding no think, making the system's prompt stricter, lowering randomness, limiting the response length, and cleaning leaked reasoning text before printing the response. Now I'm going to walk through the working version of AgentPy. This file does three main things. It loads the system prompt, it sends the request to Ollama, and it cleans the model response. The first function loads the prompt from apt prompts, system prompt MD. I kept the prompt in the prompts folder because the prompt is part of the agent's behavior. For the first test, the system prompt is very strict. It tells the model that this is a connection test, to return only the exact test requested, not to explain, not to reason, and not to include thinking. That's the first guardrail. I'm telling the model directly that this is not a creative task or a reasoning task. Next, agent.py builds the request that gets sent to Ollama. Ollama is running locally, so when this Python file sends a request there, it's talking to the local Ollama server on this computer. The request includes the model name from the env file, which is Qwen3 4b. It includes the system prompt, it includes the user prompt, and it includes a few options that make this simple test faster and clearer. Because Qwen was overthinking simple prompts, I added several guardrails. The first is enable thinking false. That setting lives in the env file. Then, in the Python code, if thinking is disabled, I add no think at the beginning of the user prompt so the model gets the message in two ways. The API setting says thinking is off, and the prompt instruction says no thinking. This helps because local models don't always behave perfectly from one setting alone. The second guardrail is the generation settings. For this test, I set temperature to 0, top P to 0.1, and num_predict to 80. Temperature controls randomness, so setting it to 0 makes the model more predictable. Top P also narrows the model's choices, which helps reduce wandering. Num_predict limits how much text the model is allowed to generate. This did take a little tuning. If the limit is too high, the model has room to ramble. If the limit is too low, the model can get cut off before it reaches the final answer. So for this test, the goal is to give it enough room to answer, but not enough room to spiral. A simple way to explain this is too much output room means a slow, rambling response. Too little output room means it gets cut off before the answer. Just enough output room gives a fast, clean response. The final guardrail is the cleanup function. Even with strict instructions, a local model might still return extra text. So before I print the response, I run it through a clean response. For this first test, I know exactly what the correct answer should be. Local model connected. So the cleanup function checks whether that phrase appears anywhere in the model's response. If it does, the function only returns that exact phrase. That makes the test deterministic. If Qwen adds extra reasoning before or after the correct answer, the app still shows only the clean result. The cleanup function also removes common thinking blocks, like text inside think tags, and it helps handle an edge case where the model only returns a closing think tag. Finally, it checks for common reasoning starters like, okay, let me think, I need to, or first. If the response starts with one of those, the app does not pretend the test passed. Instead, it returns a message saying, the model responded, but did not follow the exact output format. That matters because I want to know the difference between the model connection working and the model following the output instructions. After adding those guardrails, I run Python 3 m app.main, and now I get agent response, local model connected. That is the result I wanted. The first Python test proves the foundation works. Python can talk to Ollama, Ollama can run Quen locally, and the agent can clean the response enough to return the exact output expected. That is the stopping point for this first video. The agent's not useful yet, but the foundation is working. So this is the template I'll be using in the upcoming agent building videos. I have the link to download this from GitHub if you're interested in following along. In the next experiment, I'll start giving it actual work. The first task will be a simple email summary agent. Because the goal of this series is not AI hype. The goal is practical, local AI, small models, real tasks, private data, low overhead. That's the experiment.